So your received signal x of t, it is passed through two correlators, one giving the output x1, another correlator giving the output x2. So this received vector x, it contains x1 and x2. Let us try to understand how to draw the signal space or the constellation diagram of this type of a signal. So this is the constellation diagram for BFSK. So a constellation diagram consists of a set of all points of signals that is being transmitted. So here there are only two signals that is transmitted. One is S1 of t and other is S2 of t. S1 of t, remember that it was S1 vector consisting of root EB and 0. So along phi 1 it was root EB, and S2 corresponding to symbol 0, it is having the matrix vector as 0 and root EB. So corresponding to the coefficient of phi 1 is 0 and coefficient of phi 2 is root EB. So I have marked the two signal points S1 here and S2 here. S1 corresponds to your first symbol 1. S2 corresponds to your second symbol 0. So what we have done here is we have divided the whole constellation into two halves using the decision boundary, and observe that this decision boundary divides this constellation diagram symmetrically into two halves, exactly two halves. The reason behind this is that we assume that symbol 0 and symbol 1 are equally probable of being transmitted. So the probability of transmitting a 0 or 1 is same. So obviously the decision boundary should divide the constellation into two equal halves. Here we are actually mapping the probability as a function of space. So here there is a decision boundary. The equation for this decision boundary, it is x1 equal to x2. x1 is the output of the first correlator, which has this basis function phi 1. x2 is the output of second correlator, which has a basis function phi 2. So x1 equal to x2 defines this decision boundary. And if the value of x1 becomes greater than x2, it corresponds to this region Z1. And if the value of x2 is greater than x1, remember x2 corresponds to the second basis function phi 2. If x2 is greater than x1, then the received signal point lies somewhere in this region Z2. So if the received signal vector lies in region Z1, we decide in favor of symbol 1. And if the received signal vector x lies in region Z2, we decide in favor of symbol 0, that is defined by this point root EB. So this is the constellation diagram for BFSK. Here we have two variables, two correlator outputs, x1 and x2. So if we want to find the probability of error, we need to consider both these variables, whether x1 is greater than x2 or it is less than x2. Corresponding to that, we decide in favor of symbol 1 or symbol 0. What we are going to do is we are going to map that quantity, whether x1 is greater than x2 or the difference between x1 and x2, into a particular variable L, where L is equal to x1 minus x2. So L is equal to x1 minus x2, which means that if x1 is greater than x2, L will be positive. L will lie in a region Z1. And if L is negative, L should lie in this region Z2. So this is what I have written, and we define this random variable capital L, where the small l is a sample value from that random variable. First we are going to find the expectation of this random variable capital L, and then we are going to find the variance, because a Gaussian PDF is uniquely defined by its mean and variance. First, let's find the conditional mean of random variable capital L given that symbol 1 was transmitted. So expectation of L given that 1 was transmitted. We know that if 1 is transmitted, then x1 will have the correlator output as root EB, while x2 will be 0 at that time. But due to the addition of noise from the channel, x2 will not be a 0, or definitely not a 0, it will contain noise. But expectation of the AWGN noise, it is going to be 0. We assume the AWGN noise to have a 0 mean. So this expression will have the output as root EB. Expectation of x1 given 1 is root EB, and this will be 0. So it is root EB. Second case, when the symbol 0 was transmitted. So expectation of L given that symbol 0 was transmitted. We have x1 as 0. Expectation of x1 given 0 as 0, as x1 will contain only noise, minus x2 will have the output root EB. Expectation of x2 given 0 is minus root EB. Now finding the variance of random variable L. All these results, we have finding the mean, finding the variance here. All these results are derived from the response of bank of correlators in module 2. In module 2 we had derivations relating to this. Here we have directly taken those results. We studied from the response of bank of correlators that variance of this random variable L, it is variance of x1 plus variance of x2. We learned that the variance of the correlator output, it is independent of the transmitted signal. It only depends on the power spectral density of the transmitted signal, and we have power spectral density of the noise, not the transmitted signal. It depends on the power spectral density of noise. Here we have assumed an AWGN noise, additive white Gaussian noise, with power spectral density n0 divided by 2. So n0 by 2 plus n0 by 2 is going to give you n0. Now applying the value of mean and variance into the likelihood equation, what we get is the conditional probability density function of random variable L given that symbol 0 was transmitted. Here we assume that symbol 0 was transmitted. FL of L given 0 was transmitted, that is equal to 1 by root of 2 pi n0 e raised to minus L is a variable, minus, it should be mean. We assume that symbol 0 was transmitted. We have already obtained that a symbol 0 was transmitted, the expectation, the conditional mean is minus root EB. So L minus mean becomes L plus root EB whole square divided by 2 times variance, 2 n0. So symbol 0 was transmitted, so obviously x1 should have 0 output, x2 will have some value in it. But an error occurs when x1 is greater than x2, or in terms of L, when L is greater than 0. The conditional probability of error when symbol 0 was transmitted, it is given by P E of 0. That is, a symbol 0 was transmitted and it was erroneously received at the receiver. that is equal to probability that L is greater than 0. So when symbol 0 is transmitted, L should be less than 0, but when error happens when L is greater than 0, and then symbol 0 was sent. How do you obtain the probability from the PDF? We integrate it over L, and remember, L vary from 0 to infinity. The value of L which gives a wrong decision, it is from 0 to infinity. It is a positive value in short. So applying the result we found before into this equation and doing some substitution, L plus root EB by root 2 n0 as said, and doing some change of variables here, we obtain probability of error when symbol 0 was transmitted as 1 by 2 ERFC, complementary error function of root EB divided by 2 n0. This is a diagram of a BFSK transmitter. The incoming signal is a on-off signaling form. On-off signaling means for symbol 1 it is a plus 1 volt, for a symbol 0 it is 0 volt. So 1, it goes to these two branches. 1 goes to this branch, gets multiplied with the basis function having a frequency f1. You have frequency f1 as output of this multiplier. Same one goes here, gets inverted, becomes 0 here, and the output of this multiplier is 0. Similarly, if a binary 0 comes, it is 0 volt, gets multiplied with this multiplier, the output is 0. While it gets inverted here, the 0 gets inverted here, you have 1 here, and the output frequency of this multiplier is f2. So we understand that if the input is a binary 1, then you have the output as frequency f1. If the input is 0, you have the frequency f2. Coming to binary receiver, BFSK receiver, the input, it is given to two correlators supplied with basis functions phi1 of t and phi2 of t, integrated it over the time period tb. You have the output x1 and x2, and here we define the random variable L, which is x1 minus x2, and decision device decides in favor of 1 if L is greater than 0. It decides in favor of symbol 0 if L is less than 0. The same way we defined for constellation diagram. Also, study the waveforms relating to BFSK by yourself.